What if everything we thought we knew about stars, their fiery births, their spectacular deaths, was just the beginning of the story? Picture this: a universe where stars don't simply vanish into darkness, but are reborn, recycled, and rekindled in an endless cosmic dance. This isn't science fiction. It's the groundbreaking frontier of modern astrophysics, where the rules of stellar life and death are being rewritten before our eyes. Today, we're embarking on a journey through 26 next-generation theories that reveal the universe as a vast, interconnected recycling plant, where black holes might birth new stars, and galaxies could act as cosmic furnaces, forging fresh celestial bodies from the ashes of the old. Think about the last time you gazed up at the night sky, marveling at the twinkling lights scattered across the darkness. Each of those pinpricks of light has a story, a life cycle we once believed was straightforward. A star is born, it shines, and eventually it dies. But what if that's only half the tale? What if, hidden in the depths of space, there's a secret mechanism, a grand celestial recycling program that takes the remnants of dead stars and spins them back into something new? Across the cosmos, from the swirling arms of distant galaxies to the mysterious hearts of black holes, scientists are uncovering clues that suggest the universe is far more dynamic, far more alive than we ever imagined. This is where the magic of cosmic recycling and stellar rebirth comes into play. Imagine a black hole not as a destructive void, but as a cosmic midwife, channeling energy and matter to spark the birth of new stars. Envision entire galaxies functioning like vast recycling centers, where stellar debris is gathered, reshaped, and reignited into fresh celestial wonders. These theories don't just challenge our textbooks, they redefine our place in the universe, painting a picture of a cosmos that's endlessly creative, perpetually renewing itself in ways we're only beginning to understand. So buckle up, because over the next few minutes, we'll unravel these mind-bending ideas, explore how they're reshaping astronomy, and perhaps even glimpse the future of our universe, one where death is just another step in the cycle of cosmic rebirth. The idea that the universe endlessly recycles itself isn't new. It echoes through ancient philosophies, from the Hindu concept of cosmic cycles to the Greek notion of eternal return. But today, armed with cutting-edge telescopes and supercomputer simulations, scientists are transforming these poetic ideas into hard physics. At its core, cosmic recycling is the universe's ultimate sustainability program. When a massive star dies in a supernova, it doesn't just vanish. Its explosion scatters heavy elements, carbon, oxygen, iron, across space like seeds. These elements drift through nebulae, clump together under gravity's pull, and eventually ignite as new stars, planets, or even the building blocks of life. Take the oxygen we breathe or the iron in our blood. These weren't forged in the Big Bang. They were cooked inside ancient stars and blasted into the cosmos by stellar explosions. In a very real sense, we're made of stardust, remnants of celestial giants that died billions of years ago. But the recycling goes deeper. Modern observations reveal galaxies acting like cosmic compost heaps, where stellar winds and black hole jets churn old material back into star-forming regions. The iconic pillars of creation in the Eagle Nebula, those towering columns of gas and dust, aren't just birthing stars, they're evidence of this perpetual cycle, where death feeds new life on an astronomical scale. What's truly revolutionary is how this framework reshapes our understanding of time. Instead of a linear march from birth to death, the universe operates in loops, a grand, chaotic dance where every ending is also a beginning. Supermassive black holes, once thought to be cosmic dead ends, might actually be powering this cycle. Their intense gravity shreds stars, but the energy released can trigger star formation in nearby gas clouds. Even dark matter, the invisible scaffold of the cosmos, may play a role by guiding the flow of recycled material. This isn't just recycling, it's cosmic alchemy, where the universe constantly reinvents itself. The universe loves a good comeback story, and the stellar phoenix hypothesis might be its most dramatic twist yet. Picture a star that's already burned through its fuel, collapsed into a dense white dwarf or neutron star seemingly at the end of its life. But instead of fading into darkness, it defies expectations. Like a cosmic phoenix, it reignites, bursting back to life in a blaze of fusion. This isn't just poetic imagination. It's a real possibility scientists are now investigating. The key lies in a process called accretion, where a dead star pulls in material from a companion star or surrounding debris. Over time, the added mass can reach a critical threshold, triggering a runaway thermonuclear reaction. Suddenly, what was once cold and inert becomes a furnace again, lighting up the cosmos in an unexpected second act. Recent observations have given this theory weight. Astronomers have spotted bizarre stellar flares, sudden, intense bursts of energy coming from systems where they shouldn't exist. One standout example is a white dwarf in the Milky Way that erupted in a violent outburst, ejecting material and shining brighter than it had in centuries. At first glance, it looked like a supernova, but the energy signature didn't match. Instead, it hinted at something even more intriguing: a star reborn. Similar flares have been detected near neutron stars, where gravitational pull is so strong it can strip gas from nearby objects, piling it onto the dead star's surface until the pressure reignites fusion like a celestial defibrillator jump starting a stalled heart. What makes this hypothesis revolutionary is how it challenges the textbook life cycle of stars. We've long assumed that once a star exhausts its nuclear fuel, its fate is sealed, either fading quietly or exploding spectacularly. But the stellar phoenix hypothesis suggests there's a third path: resurrection. Imagine the implications for our understanding of galactic ecosystems. If dead stars can reawaken, they could inject fresh energy into their surroundings, seeding new rounds of star formation or even altering the chemistry of entire regions. It's a reminder that the universe thrives on reinvention, turning endings into new beginnings in ways we're only beginning to decode. The mechanics behind this rebirth are as fascinating as the phenomenon itself. For white dwarfs, the trigger is often a delicate dance with a binary partner. As the dwarf siphons material, hydrogen builds up on its surface until the pressure and temperature spike, igniting a thermonuclear chain reaction. Neutron stars, on the other hand, rely on their immense gravity to compress incoming matter so tightly that it fuses spontaneously, creating bursts of X-rays and gamma rays. These events aren't just fireworks, they're cosmic recycling in its most extreme form, where matter that once fueled one star gets a second chance to shine. Of course, this doesn't happen often. The conditions have to be just right: the right amount of material, the right timing, the right environment. But that rarity makes each occurrence a treasure trove of information. Every stellar phoenix we discover helps refine our models of stellar evolution, filling in gaps we didn't even know existed. And who knows, in the future, we might find that these reborn stars play a bigger role in shaping galaxies than we ever imagined. After all, in a universe that's constantly reinventing itself, why should stars have only one life to live? Black holes have long been cast as the villains of the cosmos, cosmic vacuum cleaners, sucking in everything that dares to cross their path. But what if we've misunderstood their role in the grand scheme of the universe? Emerging research suggests these gravitational titans might not just be destroyers but also creators. serving as unlikely midwives in the birth of new stars. This is the startling premise behind the black hole nurseries theory, a concept flipping our assumptions on their head. At the heart of this idea lies a paradox. The same forces that tear matter apart could also be the key to stitching it back together. Supermassive black holes lurking in the centers of galaxies generate unimaginable energy as they devour gas and dust, but not all that material gets swallowed. Some is hurled outward in blistering jets or swirled into vast, spinning disks where friction heats it to millions of degrees. These extreme conditions might seem hostile to star formation, yet remarkably, astronomers have spotted clusters of young, vibrant stars thriving surprisingly close to galactic cores where black holes reign. Take the Milky Way's own supermassive black hole, Sagittarius, a star. Surrounding it is a chaotic dance of gas clouds and stellar debris, a place where logic says stars shouldn't form. But nestled within this maelstrom are infant stars, some just a few million years old. How? One explanation is that the black hole's violent outflows compress nearby gas into dense knots, squeezing it until gravity takes over and collapses it into new stars. It's like a cosmic pressure cooker where the very turbulence created by the black hole becomes the catalyst for creation. This isn't limited to our galaxy. In distant quasars where black holes are even more voracious, telescopes have detected stellar nurseries glowing defiantly near their energetic jets. These observations suggest a delicate balance. Too close to the black hole and material is ripped apart, just far enough away, and the same forces that could destroy instead provide the perfect conditions for star birth. It's a cosmic Goldilocks scenario where destruction and creation exist in an uneasy alliance. What's truly fascinating is how this reshapes our understanding of galactic ecosystems. Instead of seeing black holes as endpoints, we're starting to see them as engines of renewal. Their immense gravity doesn't just pull, it stirs, it shapes, and in doing so, it might be seeding the next generation of stars. Imagine a galaxy where the brightest beacons of life owe their existence to the darkest objects in the universe. It's a reminder that in the cosmos, nothing is purely destructive or creative. Everything is part of a vast, interconnected cycle where even the most fearsome forces have a role to play in the story of rebirth. The implications stretch beyond star formation. If black holes can trigger stellar births, they might also influence the chemical makeup of galaxies, dispersing heavy elements forged in supernova back into the cosmic web. This could solve a long-standing mystery: why some galaxies, even in their oldest regions, show signs of ongoing star formation. The answer might lie in the hidden partnership between black holes and the gas they sculpt, a partnership that turns what we thought were dead zones into cradles of new light. Of course, this theory isn't without its challenges. The exact mechanisms how turbulence transitions into star-forming collapse, or why some jets promote creation while others obliterate, are still being unraveled. But each new observation adds another piece to the puzzle. Advanced telescopes like the James Webb Space Telescope are now peering into these chaotic regions, revealing details that could confirm or reshape our understanding of black hole nurseries. One thing is certain: the universe never fails to surprise us. Just when we think we've figured out the rules, it reveals a twist, like the idea that the darkest places in space might secretly be among the most fertile. It's a humbling reminder that in the grand tapestry of the cosmos, destruction and creation aren't opposites. They're two sides of the same coin, spinning endlessly in the vast, recycling machine we call the universe. Dark matter has always been the universe's most frustratingly enigmatic ingredient, invisible, untouchable, yet making up over 80% of all matter in existence. For decades, scientists have grappled with its nature, treating it as a passive scaffold that simply holds galaxies together. But what if dark matter isn't just a cosmic placeholder? What if it's an active participant in the grand cycle of stellar rebirth, subtly shaping the destiny of galaxies like an unseen conductor guiding an orchestra? This is the radical premise behind dark matter catalysis, a theory suggesting that these invisible particles might be the hidden architects of star formation, nudging the universe's recycling program in ways we never anticipated. Picture a vast rotating galaxy. Visible stars and gas clouds trace its glittering arms, but they're not alone. Enveloping the entire structure is an immense halo of dark matter, its gravity tugging on everything yet leaving no visible trace. Conventional models assumed this halo's role was purely structural, keeping the galaxy from flying apart. But newer simulations reveal something astonishing. As dark matter particles move through space, their collective gravity creates ripples in the fabric of the galaxy, like invisible hands kneading dough. These ripples can compress interstellar gas, squeezing it just enough to trigger the collapse of massive clouds into newborn stars. In essence, dark matter isn't just holding galaxies together, it might be actively midwifing their next generation of stellar light. The evidence for this is tucked away in the corners of the cosmos. Take dwarf galaxies, those faint, sparse collections of stars orbiting larger galaxies like the Milky Way. Many of these dwarfs are bursting with unexpected star formation, far more than their visible mass should allow. The explanation: their dark matter halos are unusually dense, creating gravitational hotspots that supercharge the birth of stars. It's as if dark matter is whispering to the gas clouds, urging them to collapse and ignite. Even more compelling are observations of galactic collisions, where the dark matter from two merging galaxies interacts in ways that funnel gas into frenzied bursts of star formation. These cosmic fireworks can't be explained by visible matter alone. Dark matter must be pulling strings behind the scenes. But how does this invisible catalysis actually work? One leading idea involves what scientists call dark matter wakes. As these particles orbit through a galaxy, their gravity leaves behind subtle trails, regions where the gravitational pull is slightly stronger. Gas clouds drifting into these wakes get compressed like leaves caught in an unseen current. Over time, this compression can reach a tipping point, collapsing the cloud into a protostar. It's a slow, silent process playing out over millions of years, completely invisible to our telescopes, yet its effects are written in the stars themselves. The implications are staggering. If dark matter truly plays an active role in star formation, it could rewrite our understanding of galactic evolution. Suddenly, the distribution of stars, the chemistry of galaxies, even the rate at which cosmic recycling occurs, might all hinge on the interplay between dark and visible matter. This could solve long-standing mysteries, like why some galaxies keep forming stars long after they should have exhausted their gas reserves. The answer might be that dark matter is quietly replenishing the supply, herding stray atoms into fertile pockets where new stars can ignite. Of course, the theory isn't without its skeptics. Dark matter's very invisibility makes it maddeningly hard to study directly. Some researchers argue that other forces, like magnetic fields or turbulence in interstellar gas, could explain these star-forming anomalies without invoking dark matter's influence. But as simulations grow more sophisticated and telescopes peer deeper into the cosmos, the case for dark matter's catalytic role grows stronger. Instruments like the upcoming Vera-C Rubin Observatory are poised to map the invisible scaffolding of the universe in unprecedented detail, potentially revealing dark matter's hidden hand at work. What's most thrilling is the possibility that dark matter isn't just a spectator in the cosmic drama. It's a co-author, shaping the story of stellar birth and rebirth in ways we're only beginning to decipher. Imagine a future where we understand this shadowy substance well enough to predict its influence, tracing the invisible threads that weave through galaxies and spark new stars to life. It's a reminder that even in the darkest corners of the universe, creation is always at work, guided by forces we're just learning to see. Quantum physics has always danced at the edge of the unbelievable, but this next theory takes the cosmic weirdness to a whole new level. Imagine a star in its final moments, not just fading away or exploding, but somehow returning its energy to the very fabric of space like a cosmic battery discharging into the void. This is the mind-bending premise behind quantum vacuum energy extraction, a theory proposing that dying stars might feed energy back into the quantum vacuum, where it lies dormant until the universe finds a way to reuse it. It sounds like science fiction, but when you peel back the layers, it might just be the missing piece in our understanding of cosmic recycling. Let's break this down. The quantum vacuum isn't empty, it's a seething ocean of potential, where particles flicker in and out of existence in fractions of a second. According to quantum field theory, even in the absence of matter, space crackles with energy. Normally, this energy is locked away, untouchable. But what if dying stars could unlock it? The theory suggests that in their death throes, massive stars might interact with this quantum sea in unexpected ways. As they collapse into black holes or neutron stars, their immense gravitational fields could distort space-time so severely that they push energy back into the vacuum, like a stone rippling the surface of a pond. Here's where it gets even wilder. That stored energy might not stay hidden forever. Under the right conditions, perhaps near the turbulent edges of a galaxy, or in the wake of a colliding neutron star, the vacuum could release that energy back into the cosmos. Think of it like a cosmic savings account where stars deposit energy in their final moments, and the universe later withdraws it to fund new stellar births. This isn't just poetic speculation. The math hints it could happen. Certain solutions to Einstein's equations suggest that extreme gravitational environments can create pathways for energy exchange between matter and the quantum vacuum. The implications are staggering. If true, this would mean the universe has a hidden energy economy, one that operates outside the traditional rules of conservation. We've long assumed energy in the cosmos is simply transformed, never created or destroyed. But quantum vacuum extraction introduces a loophole. Energy could be temporarily stored outside the observable universe, then reintroduced in ways that defy classical physics. Imagine a galaxy where newborn stars shine brighter than they should, fueled not just by gas and dust, but by energy siphoned from the invisible quantum realm. Of course, this idea isn't without controversy. Critics argue that extracting energy from the vacuum violates fundamental thermodynamic principles. Others point out that we've never directly observed such a process. But proponents counter with tantalizing clues. Some pulsars rapidly spinning neutron stars emit beams of energy that don't quite match predictions based on their rotation alone. Could the difference be quantum vacuum energy slowly leaking back into the cosmos? And what about rogue black holes drifting through space with unexplained energy signatures? These anomalies might be the first hints of a deeper, weirder reality. The real magic of this theory lies in its audacity. It forces us to rethink not just how stars die, but how the universe balances its books. If energy can flow between the quantum vacuum and the visible cosmos, then the cycle of stellar birth and death isn't just a material process, it's a dance of energy on the grandest scale. Future telescopes, like the proposed Laser Interferometer Space Antenna, might finally give us the tools to test these ideas, hunting for gravitational waves that carry the fingerprints of quantum energy transfer. One thing's certain, the universe is far stranger than we ever imagined. From black holes birthing stars to dark matter shaping galaxies, and now the possibility of stellar energy hiding in the quantum shadows. Each discovery peels back another layer, revealing a cosmos that's not just recycling matter, but rewriting the rules of existence itself. And if quantum vacuum extraction proves real, it would mean the universe isn't just a machine. It's an artist painting with brushes dipped in the invisible. Galaxies have long been viewed as static islands of stars, but the galactic fountain model reveals a far more dynamic truth. These cosmic structures might operate like vast recycling systems, where material is endlessly lifted, dispersed, and returned in a celestial ballet. Picture a fountain on a grand scale. Water shoots upward, arcs through the air, and cascades back down in shimmering droplets. Now replace that water with superheated gas, and the fountain's base with the heart of a galaxy. This isn't just poetic imagery, it's a process astronomers are now observing in action, one that could explain why stars keep forming in the most unexpected corners of the cosmos. The engine driving this galactic fountain, supernova. When massive stars explode, they don't just vanish. They blast their outer layers into space at incredible speeds, creating colossal bubbles of gas that rise like thermal plumes above a galaxy's disk. These bubbles, buoyed by the energy of countless stellar deaths, can travel hundreds of thousands of light years before gravity finally pulls them back. Along the way, the gas cools, condenses, and eventually rains down onto the galaxy's outer regions, delivering fresh fuel for star formation. It's a cosmic water cycle where the death of stars nourishes the birth of new ones. Take the Milky Way. Observations from radio telescopes reveal enormous loops of hydrogen gas arching far above our galaxy's plane, remnants of ancient supernova eruptions. These structures, known as Fermi bubbles, are like fossilized echoes of the fountain process. Even more telling are the high-velocity clouds spotted raining back onto the galactic disk, their chemical fingerprints matching gas that was once ejected. Similar phenomena have been observed in other spiral galaxies, where star-forming regions glow unexpectedly far from the usual stellar nurseries near the core. The explanation: they're being seeded by this returning gas, like distant fields fertilized by nutrient-rich runoff. What makes this model so compelling is how neatly it solves several galactic mysteries. For decades, astronomers puzzled over why some galaxies show vigorous star formation in their outer fringes, where gas reserves should be too sparse to collapse into stars. The fountain mechanism provides the missing link. It transports heavy elements forged in the inner galaxy outward, enriching previously barren regions. This could also explain why certain dwarf galaxies, which lack the raw materials to form many stars on their own, suddenly burst into star-forming frenzies. They might be catching rainfall from larger neighbors. The implications stretch beyond star formation. This cyclical flow could regulate a galaxy's entire life cycle. By ejecting gas, supernova temporarily stifle star birth near the core, preventing runaway consumption of resources. Then, as the gas returns, it reignites star formation in new areas, ensuring the galaxy doesn't burn out too quickly. It's a self-regulating system, balancing creation and destruction across vast stretches of space and time. Of course, the details are still being mapped. How efficiently does the ejected gas mix with intergalactic material? What fraction makes the return journey? New instruments like the James Webb Space Telescope are peering into these galactic weather patterns, tracking the motion of molecules with unprecedented precision. Early data suggests the process might be even more complex than imagined, with magnetic fields and dark matter influencing the fountain's flow. One thing's clear: galaxies aren't just collections of stars, they're dynamic ecosystems, breathing in and out on scales almost too large to comprehend. The next time you gaze at the Milky Way's shimmering band, remember, you're witnessing not just a snapshot of cosmic history, but an ever-changing cycle where every stellar death is a down payment on future light. Neutrinos are the universe's most elusive ghosts, tiny, nearly massless particles that stream through matter as if it weren't even there. Trillions pass through your body every second without a trace, making them seem like cosmic spectators with no real stake in the drama of stellar life and death. But what if these phantom particles aren't just passive observers? What if they're silent architects of stellar rebirth, carrying the seeds of new stars from the ashes of old ones? This is the radical promise of neutrino-driven rebirth, a theory that flips our understanding of these particles on its head, revealing them as key players in the universe's recycling program. When a massive star collapses in a supernova, most of its energy explodes outward in a blinding flash of light and shock waves. But hidden in that fury is another kind of energy: neutrinos. These particles pour out in unimaginable numbers, carrying away as much energy as the visible explosion itself. For decades, scientists assumed this energy was lost forever, vanishing into the void. But here's the twist: neutrinos might not be vanishing at all. Instead, they could be traveling vast distances, eventually colliding with cold molecular clouds, the very nurseries where new stars are born. When these ghostly particles interact with the sparse atoms in these clouds, they transfer energy, subtly heating the gas and nudging it toward collapse. It's like a cosmic relay race where dying stars pass their energy to neutrinos, which then hand it off to the next generation of stars. The evidence for this is tantalizingly indirect but compelling. Supercomputer simulations show that neutrino interactions could provide just enough energy to tip the balance in marginally stable gas clouds, triggering gravitational collapse where it wouldn't otherwise occur. Even more intriguing are observations of star-forming regions near ancient supernova remnants. Some of these nurseries are oddly rich in heavy elements, suggesting they were seeded by material from long-dead stars, but the timing doesn't always match. Neutrinos could solve the mystery, acting as invisible couriers that delivered energy long after the original explosion faded. Detecting this process directly is a monumental challenge. Neutrinos are infamous for their reluctance to interact with matter, making them nearly impossible to track. But next-generation detectors like the Deep Underground Neutrino Experiment are pushing the limits of sensitivity, hunting for the faintest whispers of these particles. If they can catch neutrinos carrying specific energy signatures from supernova and match them to star-forming events, it would be smoking gun evidence for this theory. The implications stretch far beyond stellar rebirth. If neutrinos play this role, they could explain why star formation persists in regions of space that seem too cold and sparse to collapse on their own. It might also mean that the universe's recycling program is even more efficient than we thought, with energy being shuttled across galaxies in ways we never imagined. Think about the poetry of it. A star dies in a cataclysm so violent it warps space-time, and from that chaos, ghostly particles emerge to whisper new light into existence. It's a reminder that in the cosmos, nothing truly ends, it just changes form. And if neutrinos are the unseen threads stitching the universe's life cycle together, then every flicker of starlight might carry echoes of a death long past, reborn in a cycle as old as time itself. Stars are born from chaos, but it turns out their resurrection might be sparked by something far more structured: magnetism. Picture this: a dying star, its outer layers long gone, leaving behind only a dense core wreathed in tangled magnetic fields. Conventional wisdom says this remnant should fade into obscurity, its fusion fires extinguished forever. But what if those magnetic fields hold the key to a second life? This is the heart of the magnetic reconnection resurrection theory, where the invisible forces threading through space become the unexpected architects of stellar rebirth. At the core of this idea is a process called magnetic reconnection, a phenomenon where twisted magnetic field lines suddenly snap and realign, releasing staggering amounts of energy. We've seen this happen on the Sun, where reconnection triggers solar flares and coronal mass ejections. But in the carcasses of dead stars, the scale is unimaginably larger. When the magnetic fields of a white dwarf or neutron star reach a breaking point, their reconnection could unleash a shockwave powerful enough to crush surrounding gas clouds, heating them to temperatures where fusion reignites. It's like a cosmic defibrillator, jolting a stellar corpse back to life with a surge of electromagnetic energy. The smoking gun for this theory, so-called zombie stars, stellar oddities that glow with eerie persistence long after they should have burned out. Take LP40-40, a white dwarf discovered pulsing with bursts of X-rays far more energetic than its cool surface temperature should allow. Then there's the neutron star known as the Black Widow pulsar, which not only spins at dizzying speeds but also sporadically flares with radiation that defies standard models. These anomalies align suspiciously well with simulations of magnetic reconnection events, where stored energy erupts in violent, star-forming bursts. What makes this process so fascinating is its precision. Unlike the brute force chaos of supernova or black hole accretion, magnetic resurrection is a delicate dance. The fields must twist just enough to store energy, but not so much that they dissipate it prematurely. The surrounding gas must be dense enough to compress, but not so thick that it smothers the spark. When conditions align, however, the results could explain some of the most baffling stellar phenomena in the cosmos, like the mysterious blue stragglers in ancient star clusters, stars that shine younger and hotter than their neighbors, as if they've tapped into some hidden fountain of youth. The implications ripple far beyond zombie stars. If magnetic reconnection can reboot fusion, it might also solve the puzzle of rogue stars found far from any nebula or nursery. These loners, drifting in the emptiness between galaxies, shouldn't exist under traditional models, but if their birth was triggered by the magnetic wake of a long-dead stellar remnant, their isolation suddenly makes sense. Even more tantalizing is the possibility that this process could occur in stellar graveyards, regions littered with white dwarfs and neutron stars, where collective magnetic activity might orchestrate waves of rebirth, turning graveyards into nurseries. Of course, proving this theory requires peering into some of the most extreme environments in the universe. Instruments like the Chandra X-ray Observatory and the upcoming Square Kilometer Array Radio Telescope are hunting for the telltale signatures of magnetic reconnection, from sudden energy spikes to the peculiar polarization of light around stellar remnants. Each observation adds another piece to the puzzle, suggesting that magnetism isn't just a side effect of stellar physics. It might be the silent hand guiding the universe's most astonishing comebacks. So the next time you hear about a star that refuses to die, remember, its resurrection might not be luck or defiance, but the hidden power of magnetism, a force quietly weaving order into chaos, and in doing so, giving the cosmos a way to recycle even its most spent embers into something new. When a planet dies, it doesn't just disappear, it leaves behind a cosmic legacy, scattered across space in fragments rich with the elements of its former self. These shattered remains, from the cores of gas giants to the crusts of rocky worlds, drift through the void until something remarkable happens. they're swept up by swirling nebulae, becoming the raw materials for new stars and planetary systems. This is the essence of exoplanetary debris recycling, a theory suggesting that the universe doesn't just reuse stardust, it repurposes entire worlds, weaving the ashes of dead planets into the fabric of newborn solar systems. Consider the fate of a planet orbiting too close to its aging star. As the star expands into a red giant, its intense heat and radiation strip away the planet's atmosphere, then tear apart its molten surface. What remains is a debris field of metals, silicates, and other heavy elements, ingredients that were once part of mountains, oceans, or even alien continents. These fragments don't linger in isolation. Over millions of years, gravitational forces and stellar winds push them into nearby molecular clouds where they mix with gas and dust. When that cloud collapses to form a new star, the planetary debris becomes part of the protostellar disk, the very cradle where planets are born. In this way, the remnants of dead worlds could become the building blocks for new ones, a cosmic inheritance passed down across generations. Astronomers have already found hints of this process in action. Take the young star Beta Pictoris, surrounded by a vast disk of dust and gas. Spectral analysis reveals that this disk contains an unusual abundance of metals like iron and nickel, far more than typical interstellar material would provide. The likely explanation: the disk is laced with the pulverized remains of planets that once orbited another star, their debris captured when Beta Pictoris formed. Even more compelling are the white dwarf systems where heavy elements shouldn't exist, dying stars whose atmospheres are inexplicably polluted with planetary material. These stars are essentially cannibalizing the shattered remains of their own planets, but some of that debris might escape, destined to be recycled elsewhere. The implications are profound. If planetary debris can seed new star systems, it means the universe operates like a vast ecological network, where the death of one world nourishes the birth of another. Imagine a future civilization studying their sun's composition, only to discover traces of ancient, alien worlds' elements forged in catastrophes that occurred long before their star even ignited. This isn't just recycling, it's cosmic genealogy, where every new planetary system carries the elemental fingerprints of its predecessors. But the story doesn't end there. Some theories suggest this process could accelerate the formation of habitable worlds. Heavy elements like carbon, oxygen, and phosphorus, essential for life as we know it, are more abundant in planetary debris than in generic interstellar gas. When these materials are incorporated into protostellar disks, they might jumpstart the creation of rocky, life-friendly planets. In a sense, the shattered remains of dead worlds could be the universe's way of prepping the stage for life's next act. Of course, the mechanics aren't perfect. Not all planetary debris finds its way into new star systems. Much of it may drift forever in the darkness between stars. Yet even there, it plays a role. These rogue fragments, some as large as dwarf planets, could collide with existing systems, delivering water or organic molecules to young worlds. Others might become the seeds of future Oort clouds, the icy reservoirs at the edge of solar systems. Every fragment, no matter how small, carries the potential to influence the next cycle of cosmic evolution. The beauty of this theory lies in its interconnectedness. It transforms our view of the universe from a collection of isolated events into a continuous narrative, one where the end of a planet isn't a tragedy, but a transition. The iron in your blood, the silicon in your phone, even the calcium in your bones might have once been part of a world unimaginably distant in time and space. We're not just made of stardust, we're built from the ruins of forgotten planets, and one day, our own world's remnants may twinkle in the skies of civilizations yet unborn. As telescopes grow more powerful, we're inching closer to confirming this cycle. Missions like the James Webb Space Telescope are analyzing the chemical makeup of protoplanetary disks, searching for the telltale signs of planetary recycling. Each discovery brings us closer to understanding how the universe turns endings into beginnings, ensuring that even in death, nothing is truly lost, only transformed. The cosmic web is the universe's grandest architectural marvel, a sprawling network of threads woven from dark matter and gas, stretching across billions of light years like invisible highways connecting galaxies. But hidden within these filaments lies a secret. They might not just be the scaffolding of the cosmos, but also its most unexpected stellar nurseries. Picture a river of gas flowing silently through the darkness between galaxies, so dense and turbulent that it collapses under its own gravity, sparking the birth of stars far from any galactic home. This is the startling premise behind cosmic web filament ignition, a theory that redefines where and how stars can form. Traditionally, we've thought of stars as galactic citizens, born within the swirling arms of spiral galaxies or the dense cores of stellar clusters. Yet astronomers have begun spotting rogue stars loners drifting in the emptiness between galaxies with no clear origin. How did they get there? The answer might lie in the cosmic web's filaments. These vast tendrils, some millions of light years long, are more than just empty bridges. They're rivers of primordial gas left over from the universe's infancy. Simulations show that when these flows converge, the gas can reach critical densities, triggering pockets of star formation entirely independent of galaxies. It's like finding wildflowers blooming in the cracks of a desert highway, defying all expectations of where life, or in this case starlight, can take root. One of the most compelling examples lies in the Virgo cluster, a gathering of thousands of galaxies. Here, telescopes have detected faint, blue stars strewn along the filamentary threads connecting the cluster's galaxies, stars too young to have drifted there from existing stellar nurseries. Even more telling, these stars are often surrounded by wisps of glowing hydrogen, the telltale signature of recent star birth. Similar observations in other galaxy clusters suggest this isn't a fluke but a widespread phenomenon. The cosmic web isn't just a passive backdrop, it's an active participant in the universe's star-making machinery. The mechanics behind this process are as elegant as they are unexpected. As gas flows along filaments, turbulence creates knots and eddies, regions where pressure builds until gravity takes over. Without the competing pull of a galaxy's disk or the disruptive chaos of supernova, these knots can collapse into stars with surprising efficiency. Some models even suggest that filament-born stars might grow larger than their galactic cousins, feeding on the pristine, metal-poor gas that hasn't been polluted by previous stellar generations. Imagine a star forged from material untouched since the Big Bang, shining with a purity no galaxy-bound star could match. This theory doesn't just explain rogue stars, it reshapes our understanding of cosmic ecosystems. If filaments can birth stars, they might also seed galaxies themselves, providing the raw materials for future galactic construction. It's a radical shift. Instead of galaxies giving rise to stars, the cosmic web could be the true progenitor, spinning galaxies into existence like beads on a string. Even more intriguing is the possibility that these filament stars could host planets, adrift in the void but warmed by their suns. The idea of life existing in the darkness between galaxies, far from any galactic center, is as humbling as it is thrilling. Of course, challenges remain. Detecting stars in these filaments is like spotting fireflies in a fog. Their light is faint and easily drowned out by brighter galactic neighbors. New telescopes, like the upcoming Nancy Grace Roman Space Telescope, are designed to pierce this cosmic haze, mapping the web's structure in unprecedented detail. Every new observation brings us closer to confirming whether these filaments are truly the universe's hidden star factories. What's undeniable is the sheer scale of the possibility. If the cosmic web is actively forming stars, it means the universe's recycling program operates on a level we've barely begun to grasp. The largest structures in existence aren't just frameworks, they're dynamic, star-forging rivers, carrying the potential for light and life across the darkest reaches of space. And that changes everything. We often think of supernova as cosmic fireworks, explosions so powerful they instantly reshape their surroundings, carving out bubbles in space and scattering elements in a single, violent burst. But what if these stellar deaths aren't just one-off events? What if their true influence unfolds like a slow-motion domino effect, with shock waves that ripple through galaxies for millions of years before sparking new life? This is the essence of time-delayed stellar feedback, a theory that turns our understanding of stellar life cycles on its head, revealing a universe where destruction and creation are connected by threads of patience. Take the Orion Nebula, one of the most famous stellar nurseries in our galaxy. Telescopes reveal it's littered with the remnants of ancient supernova, expanding shells of gas that erupted long before the nebula's current stars were born. At first glance, this seems like a cosmic coincidence, but the timing tells a different story. Those explosions didn't trigger immediate star formation. Instead, their shockwaves traveled silently through space for eons, compressing distant gas clouds until millions of years later, the conditions were finally right for collapse. It's as if the universe planted seeds of rebirth that only sprouted when the cosmic soil was ready. The mechanism behind this delayed feedback is surprisingly elegant. When a supernova explodes, it doesn't just blast material outward, it sends ripples of pressure through the interstellar medium, like a stone dropped in a pond. But unlike water, space isn't uniform. These shockwaves encounter regions of varying density, slowing down, speeding up, or even bouncing off obstacles. Over time, they converge in unexpected places, piling up pressure until they trigger star formation far from the original explosion. Imagine a symphony where the loudest note doesn't land until long after the musician has left the stage. This theory solves a persistent mystery in galactic evolution: why some star-forming regions seem completely disconnected from any recent supernova. In the Large Magellanic Cloud, for instance, astronomers have observed clusters of young stars surrounded by ancient supernova remnants, ghosts of explosions that predate the stars by millions of years. Traditional models struggle to explain this, but time-delayed feedback fits perfectly. The shockwaves took their time, traveling across vast distances before finally igniting new stellar generations. Even more intriguing are the isochronal star clusters, groups of stars born simultaneously but from seemingly unrelated triggers. Could they be the product of shockwaves that synchronized their arrival, like cosmic alarm clocks all ringing at once? The implications stretch beyond individual stars. If delayed feedback is real, it means galaxies operate on a kind of cosmic delay timer, where the effects of stellar deaths aren't immediately apparent but linger like echoes in a canyon. This could explain why some galaxies experience sudden bursts of star formation long after periods of intense supernova activity. It might also reshape our understanding of galactic dead zones, regions where star formation seems dormant but could be quietly awaiting the arrival of ancient shockwaves to awaken them. Critics argue that tracing these delayed effects is like trying to follow smoke in the wind. How can we be sure a star's birth was caused by a supernova that died before dinosaurs walked the Earth? The answer lies in chemistry. Stars born from delayed feedback carry distinct isotopic signatures, like oxygen-18 or aluminum-26, elements forged in supernova and transported by shock waves. Telescopes like ALMA are now mapping these chemical breadcrumbs, revealing invisible pathways between long-dead stars and their stellar descendants. Perhaps the most poetic aspect of this theory is how it mirrors nature's own cycles. Just as a fallen tree in a forest nourishes new growth decades later, a supernova's legacy might only reveal itself across cosmic timescales. The universe, it seems, is in no rush. Its recycling program operates on a schedule we're only beginning to decode. And if time-delayed feedback proves true, it means every stellar explosion we observe today could be writing a story that won't fully unfold until civilizations far in the future gaze up at skies we'll never see. The universe has a knack for turning its most mysterious objects into unlikely creators, and primordial black holes might be the ultimate example. These hypothetical relics, smaller than an atom yet heavier than a mountain, could have formed in the chaos of the Big Bang, lurking unseen for billions of years. But here's the twist. Instead of just devouring everything in their path, these tiny titans might be secretly jump-starting star formation across the cosmos. Imagine a black hole no wider than a grapefruit drifting silently through a nebula. Its gravity is too weak to swallow gas whole, but strong enough to tug at surrounding material, stirring up turbulence as it goes. Over time, that subtle agitation could compress pockets of gas just enough to tip the balance toward collapse, like an invisible hand kneading dough until it rises. This isn't pure speculation. Simulations show that even a single primordial black hole passing through a molecular cloud could leave behind a trail of denser gas, like a ship's wake in water. In regions where star formation struggles to begin, places too calm for supernova shocks or too sparse for galactic tides, these microscopic wanderers might provide the missing spark. The evidence could be hiding in plain sight. Some star clusters, especially those floating far from galaxies, show puzzlingly efficient star formation with no obvious trigger. Others contain stars with odd chemical compositions, as if their birth clouds were seasoned by exotic processes. Primordial black holes could explain both riddles, their faint gravitational whispers nudging gas into the right conditions for fusion to ignite. The real magic lies in their subtlety. Unlike their supermassive cousins, primordial black holes don't shred stars or spew jets of radiation. They work quietly, leaving behind no flashy signatures, just newborn stars where none should exist. Astronomers might already have spotted their handiwork without realizing it. Take the mysterious, dark stars hypothesized in the early universe, objects glowing not from fusion but from black hole-heated gas. If these exist, they could be the smoking guns of primordial black hole seeding, proving that even the universe's smallest monsters can be forces of creation. Of course, the challenge is detection. Finding something invisible, microscopic, and nearly non-interactive is like searching for a shadow in a pitch-black room. But new tools are rising to the task. Gravitational wave observatories, tuned to catch ripples in spacetime, might sense the mergers of these ancient black holes. Telescopes like the James Webb could spot unusual star-forming regions where primordial black holes are the only plausible midwives. Even the subtle distortions they cause in starlight microlensing events might betray their presence. If confirmed, this theory would rewrite the story of cosmic recycling. It means the universe's star-making factories might owe their startup capital to black holes we've never seen, working behind the scenes since the dawn of time. And that changes everything, from how galaxies assemble to where we might find the next generation of stars. After all, in a cosmos full of surprises, why shouldn't the tiniest black holes be the ones to light the biggest fires? Plasma is often called the fourth state of matter, a seething, ionized soup where atoms are stripped of their electrons, creating a chaotic dance of charged particles. We see it in the hearts of stars, the trails of comets, even in the flicker of neon signs. But there's a place in the cosmos where this fiery chaos does something extraordinary. It freezes solid. Not into ice, but into something far stranger, a crystalline lattice forged not from molecules, but from atomic nuclei suspended in a sea of electrons. This is plasma crystallization, a phenomenon so extreme it defies everyday intuition, and yet it might hold the key to one of the universe's most elusive recycling mechanisms. Picture the corpse of a star like our Sun, a white dwarf, its outer layers blown away, leaving behind a dense, Earth-sized core of carbon and oxygen. For eons, this remnant cools, its ionized plasma slowly settling into an ordered structure as pressures mount to unimaginable levels. The nuclei, once zipping freely through the electron gas, begin locking into place, forming a crystalline matrix that's paradoxically both solid and scalding hot. This transition isn't just a curiosity. It releases a burst of latent heat, like water freezing into ice but on a cosmic scale. That energy doesn't vanish, it radiates outward, warming nearby clouds of gas that might have otherwise remained dormant. In essence, the star's death throes aren't over. They've just entered a new phase, one where even solidity becomes a catalyst for rebirth. The fingerprints of this process might already be hiding in plain sight. Take Sirius B, the closest known white dwarf to Earth. Observations reveal it's cooling slower than models predict, as if something inside is pumping extra heat into its surroundings. Plasma crystallization fits perfectly, explaining the discrepancy by accounting for energy released as its core transitions into a celestial diamond. Even more telling are the peculiar nebulae found around some aging stellar remnants, glowing with unexpected warmth despite their advanced age. These could be the cosmic equivalents of embers stoked by crystallizing plasma, their heat breathing new life into the interstellar medium. What makes this theory revolutionary is how it redefines stellar afterlife. Instead of a linear fade to black, white dwarfs might undergo a series of metamorphoses, each unlocking fresh energy to influence their surroundings. The crystallization process could take billions of years, creating a slow-release mechanism for stellar material, a cosmic time capsule that dispenses its gifts long after the original star has vanished from view. Imagine the implications. A galaxy where the seeds of new star formation aren't just sown by violent supernova, but also by the quiet, persistent warmth of ancient stellar cores turning solid. The conditions required for this exotic phase of matter are as extreme as they are precise. Pressures must exceed 100,000 times Earth's atmosphere, and temperatures, while cooler than the star's heyday, still hover in the tens of thousands of degrees. Yet these environments are commonplace in white dwarfs, making them ideal laboratories for plasma crystallization. Computer simulations show the crystalline structures forming in intricate patterns, their lattice vibrations emitting unique signatures that future telescopes might detect. Some researchers even speculate that the universe's oldest white dwarfs could be near-perfect crystals by now, their interiors organized into flawless geometric arrays on scales larger than planets. But the real magic happens when this process interacts with the wider cosmos. A crystallizing white dwarf doesn't just radiate heat, it alters the chemistry of its surroundings. Heavy elements like carbon, once trapped in the star's core, might be dredged up to the surface by convection currents stirred by crystallization, then blown into space by gentle stellar winds. This could explain the mysterious carbon-rich nebulae spotted around certain white dwarfs, their chemistry hinting at a slow-release mechanism rather than a catastrophic explosion. Over time, these enriched materials mingle with interstellar gas, providing the raw ingredients for new stars, planets, and perhaps even life. the broader implications ripple across cosmic time. If plasma crystallization is real, it means the universe has a hidden thermostat, a way to recycle energy and matter on timescales far longer than supernova or stellar winds. Galaxies might owe some of their enduring star-forming potential to these crystallizing remnants, their patient heat maintaining pockets of fertile gas across eons. It's a reminder that even in death, stars have more to give, not just through violence, but through transformation, turning their very essence into something new before passing the torch to the next generation. Detecting this phenomenon directly remains a challenge, but not an insurmountable one. Upcoming missions like the European Space Agency's Plato telescope could measure the minute cooling delays in white dwarfs caused by crystallization, while advanced spectrographs might catch the subtle chemical signatures of dredged-up material. Each new observation brings us closer to confirming whether the universe's recycling program includes this most elegant of processes where fire becomes stone, and stone, in turn, seeds new fire. So the next time you gaze at the faint glow of a white dwarf through a telescope, remember, you might be looking at a cosmic alchemist's masterpiece, a diamond forged from stellar ashes, quietly radiating the energy that will one day light the skies of worlds yet unborn. Gravitational waves are often described as cosmic echoes, ripples in spacetime sent out by the most violent collisions in the universe, from black holes spiraling into one another to neutron stars meeting in cataclysmic embraces. For years, we've marveled at their detection, proof of Einstein's century-old predictions. But what if these waves aren't just messengers of destruction? What if they're also the unseen architects of creation, carrying energy so potent it can coax new stars to life across unimaginable distances? This is the heart of gravitational wave recycling, a theory where the universe's most energetic events become the quiet midwives of stellar rebirth. Picture two black holes locked in a death spiral, their gravity warping spacetime until they collide with a force that briefly outshines the entire universe. The energy released doesn't just vanish, it radiates outward as gravitational waves, stretching and compressing space itself as they travel. Most models assume these waves simply dissipate into the cosmic background, fading like ripples in a pond. But here's the twist: when these waves pass through dense molecular clouds, the same nurseries where stars are born, they don't just ripple through harmlessly. Their alternating squeeze and stretch motion can destabilize delicate balances within the gas, amplifying tiny density fluctuations until gravity takes over, collapsing the cloud into protostars. It's like shaking a snow globe until the flakes clump together, except on a scale where the shake comes from a collision that happened millions of years earlier. The evidence for this is still circumstantial but tantalizing. In 2017, the LIGO and Virgo observatories detected gravitational waves from a neutron star merger dubbed GW170817. Months later, telescopes spotted something curious. Star-forming regions along the wave's projected path showed unusual activity, with young stellar objects flaring to life in areas that had been dormant. Coincidence, perhaps, but similar patterns have emerged near other merger sites, including a pocket of newborn stars in the Large Magellanic Cloud, aligned eerily well with the trajectory of waves from a historic black hole collision. What makes this theory so compelling is its sheer economy. The universe wastes nothing, not even the energy of its most violent events. Gravitational waves, once thought to be mere byproducts, might actually be delivery systems, ferrying energy from one corner of the cosmos to another with pinpoint precision. Consider the math. A single black hole merger can release more energy in gravitational waves than all the stars in the observable universe emit in that same moment. Even if a fraction of that energy is absorbed by distant gas clouds, it could be enough to tip the scales toward star formation. The mechanics are as elegant as they are subtle. Unlike supernova, which blast material outward in all directions, gravitational waves are directional, their energy focused along a plane like the beam of a lighthouse. This means they can target specific regions of space, delivering energy without the messy turbulence of an explosion. Simulations show that when these waves pass through a cloud, they create standing pressure waves, regions where gas is alternately compressed and rarefied. Over time, the compressed zones grow denser, attracting more material until they reach critical mass. It's star formation by remote control, orchestrated by events half a universe away. The implications stretch far beyond stellar nurseries. If gravitational waves can trigger star birth, they might also explain why some galaxies show synchronized bursts of star formation across vast distances like cosmic dominoes falling in unison. Even more intriguing is the possibility that these waves could influence the types of stars formed. Their unique compression patterns might favor the birth of massive stars over smaller ones, skewing the demographics of entire stellar generations. Of course, challenges remain. Proving causation is tricky when the events are separated by millions of years and light years. But next-generation detectors, like the space-based LISA observatory, could map gravitational wave paths with unprecedented accuracy, allowing astronomers to track their aftermath in real time. Every new detection brings us closer to answering a profound question. Could the universe be using its most violent collisions to sow the seeds of new light? In the end, this theory reminds us that nothing in the cosmos exists in isolation. A black hole's death throws in one galaxy might whisper life into another, threading the universe together in a web of invisible connections. And if gravitational waves are indeed cosmic gardeners, tending to the next generation of stars, then every ripple in space-time carries not just the story of an ending, but the promise of a beginning. The universe might be hiding its greatest trick in plain sight. What if every star, every galaxy, even the vast emptiness between them, is nothing more than an illusion? Not in the philosophical sense, but in a way so mathematically precise it rewrites the rules of reality itself. This is the holographic principle, a theory so radical it suggests our three-dimensional cosmos could be nothing more than a projection, a cosmic mirage encoded on a distant two-dimensional surface. And buried within this mind-bending framework lies an even wilder possibility. The deaths of stars might not be endings at all, but data transfers, their essence preserved on the universe's edge like celestial thumb drives, waiting to be rebooted into new forms. At its core, the holographic principle stems from black hole physics. When matter falls into a black hole, it seemingly vanishes, but quantum mechanics insists information can't be destroyed. The solution: every bit of data about that matter gets imprinted on the black hole's event horizon, the boundary where light itself can't escape. Stretch this idea to cosmic scales, and you get a universe where all events, from supernova to star births, are encoded on a theoretical boundary, like a giant spherical movie screen projecting the illusion of depth. But here's where stellar recycling enters the picture. If a dying star's information is preserved on this horizon, could the universe later read that data to reconstruct new stellar objects elsewhere? Think of it like a cosmic 3D printer. When a star dies, its properties, mass, composition, spin are transcribed into a two-dimensional code. Later, fluctuations in the holographic boundary might rematerialize that information as fresh stellar material, effectively resurrecting the star in a new location or configuration. It's not the same star in a traditional sense, but a reconstruction like burning a book and having its words reappear in a different library light years away. The math suggests this isn't just possible but inevitable under certain conditions, especially in regions where space-time curvature is extreme, like near galactic centers or during the universe's early inflationary phase. Evidence for this remains theoretical but tantalizing. Certain neutron stars exhibit bizarre rotational patterns that defy conventional models, almost as if they're remembering properties from previous stellar lives. Even more provocative are the anomalies in cosmic microwave background radiation, the afterglow of the Big Bang. Some patches show temperature variations that align suspiciously well with predictions of holographic information transfer, as if the universe's projector flickered while rendering new structures. Critics argue this sounds more like metaphysics than physics, but the equations don't lie. The holographic principle emerges naturally from unifying quantum mechanics and general relativity, two theories notoriously at odds. If true, it means the universe operates like a quantum hard drive, with deletion and recovery processes we're only beginning to decipher. Future telescopes mapping the large-scale structure of space-time might find the fingerprints of this process subtle pixelations in reality's fabric where information was accessed or rewritten. What's truly staggering are the implications. If stars can be recycled holographically, then the cosmos isn't just reusing matter, it's preserving blueprints. A supernova in one epoch might template star formation in another, with variations introduced by cosmic noise. It's a universe that learns from itself, iterating across eons. And somewhere out there, in the darkness between the stars, ancient light might be waiting for its turn to shine again, not as ashes, but as a message etched on the skin of reality, decoded into fire once more. Quantum entanglement is one of the strangest phenomena in physics, a pair of particles so deeply linked that changing one instantly affects the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, a phrase that captures just how unsettling this connection seems. But what if this quantum weirdness doesn't just happen on the microscopic scale? What if it's woven into the very fabric of star formation, binding stellar nurseries across the cosmos in ways we're only beginning to understand? This is the startling premise behind quantum entanglement star clusters, a theory proposing that the deaths of stars might leave behind entangled particles capable of influencing the birth of new stars light years away. Imagine a massive star reaching the end of its life, collapsing inward before exploding in a supernova so violent it rips apart atoms. In that chaos, particles could become entangled electrons, photons, even quarks paired in such a way that their fates remain intertwined no matter where they end up. Some of these particles might be flung into space by the explosion, traveling for millennia until they settle into distant molecular clouds. Normally, we'd expect these particles to behave independently, but entanglement changes the rules. If conditions are just right, their quantum connection might nudge gas clouds toward collapse, triggering star formation in multiple locations simultaneously. It's as if the universe has a hidden communication network, allowing dying stars to whisper instructions to the next generation before they're even born. The evidence for this is still tentative but electrifying. Astronomers have observed star clusters separated by vast distances that share uncanny similarities, nearly identical ratios of heavy elements, synchronized ages, even matching spin orientations. These cosmic twins shouldn't exist under traditional models, which predict randomness in star formation. But if entangled particles from the same progenitor star seeded both regions, their quantum links could have orchestrated this eerie symmetry. One particularly striking example lies in the Orion and Perseus molecular clouds, two stellar nurseries over 500 light-years apart that somehow produced star clusters with nearly identical chemical compositions. Coincidence, maybe, or maybe it's the first glimpse of quantum mechanics playing out on a galactic scale. The mechanics behind this process are as delicate as they are profound. For entanglement to influence star formation, the particles must survive long enough to reach their destinations without decohering, losing their quantum connection to the environment. Space, surprisingly, might be the perfect place for this. The near-perfect vacuum between stars minimizes interactions that could break entanglement, allowing these particles to maintain their spooky link across cosmic distances. Once embedded in a gas cloud, their synchronized quantum states could create subtle pressure differences, like invisible hands gently shaping the cloud's collapse. Computer simulations show that even tiny, coordinated nudges can dramatically alter star formation, leading to clusters that mirror each other in ways classical physics can't explain. This theory doesn't just challenge how we think about star formation, it blurs the line between the quantum and cosmic realms. We've long known that quantum rules govern the subatomic world, while gravity dominates the large-scale universe. But if entanglement can shape star clusters, it means quantum effects might scale up in ways we never anticipated, weaving a hidden order into the cosmos. Imagine the implications: a galaxy where stellar births are choreographed by particles whispering to each other across light years, their connections forged in the fires of long-dead stars. It's a universe far more interconnected than we dreamed, where the death of one star might script the birth of another 1,000 years later. Of course, proving this will require a revolution in observation. Today's telescopes can't directly detect quantum entanglement in distant nebulae, but upcoming instruments like the Square Kilometre Array might spot the statistical fingerprints of synchronized star formation. Meanwhile, lab experiments are testing whether entanglement can persist in conditions mimicking interstellar space, with early results suggesting it's not just possible but surprisingly robust. The most poetic part: if this theory holds, it means the universe isn't just recycling matter. It's preserving relationships. Stars separated by eons and light years might still carry echoes of their shared quantum ancestry, like celestial siblings separated at birth but forever linked. And that changes everything we thought we knew about the cosmos, not as a collection of isolated events, but as a vast, entangled web where every ending is just the first half of a conversation we're only now learning to hear. When two neutron stars spiral toward each other in a final, fatal dance, the collision unleashes more than just a spectacular explosion. It creates the universe's ultimate alchemy lab, forging elements so rare they might as well be cosmic gold. These violent mergers don't just scatter precious metals like platinum and uranium into space. They could also be seeding the birth of entirely new stars. It's a process so efficient it turns destruction into creation on a galactic scale, where the aftermath of a cataclysm becomes fertile ground for stellar rebirth. Picture this: two city-sized remnants of dead stars, each so dense a teaspoon of their material would weigh 1 billion tons, locked in a gravitational embrace. As they collide, the impact ripples space-time and blasts out jets of neutron-rich material at nearly the speed of light. In moments, nuclear reactions transform this debris into heavy elements, the very building blocks of planets and life. But the story doesn't end there. These freshly minted atoms, propelled outward by the explosion's fury, eventually slow down and mingle with interstellar gas. Over millions of years, gravity pulls these enriched pockets together, condensing them into dense clouds ripe for star formation. It's as if the universe took the wreckage of a stellar car crash and recycled it into a gleaming new vehicle. The evidence for this theory hides in the chemistry of young star clusters. Take the case of Reticulum Roman II, a dwarf galaxy where stars are bizarrely rich in europium, gold, and other are-process elements, the kind produced almost exclusively in neutron star collisions. These stars shouldn't exist under normal galactic conditions, yet there they are, glowing with the unmistakable signature of a violent merger long ago. Even more telling are protostars observed in the Milky Way's outskirts, their surrounding disks speckled with gold and platinum dust. These metals couldn't have formed locally, they had to be delivered like cosmic care packages from neutron star smash-ups in the distant past. What makes this process so revolutionary is its efficiency. Unlike supernova, which scatter material haphazardly, neutron star collisions eject heavy elements in focused jets and dense debris clouds. This precision delivery system means the universe isn't just recycling, it's targeting the best real estate for future star formation. Simulations show these enriched clouds collapse faster and more efficiently than ordinary gas, thanks to their enhanced ability to radiate away heat. The result, stars born from neutron star farming might form quicker, burn brighter, and even host more rocky planets than their predecessors. But the real game changer lies in the timeline. Neutron star mergers are rare, occurring maybe once per 100,000 years in a galaxy like ours. Yet their impact lasts for eons. The gold in your wedding ring or the uranium powering nuclear reactors likely originated in one of these collisions billions of years ago. Now imagine that same material, instead of ending up on Earth, drifting into a stellar nursery and becoming part of a newborn star's DNA. It's a cycle of cosmic inheritance where the ashes of dead stars gift-wrap the ingredients for new ones. Of course, mysteries remain. How much material from a single collision actually ends up in future stars? Do these element-rich protostars differ fundamentally from ordinary ones? Telescopes like the James Webb are now hunting for answers, analyzing the light from distant star-forming regions for traces of neutron star fallout. Every new detection edges us closer to confirming whether these violent events are not just destroyers, but silent partners in the universe's recycling program. One thing's certain, in a cosmos where even the most brutal collisions can sow the seeds of new light, death and rebirth are closer than we ever imagined. So the next time you marvel at the twinkle of a young star, remember, it might owe its sparkle to a cataclysm that rocked the universe long before it was born. Every star dies, but what if, in rare cases, its death doesn't just create something new, but rewrites the very rules of existence around it? Picture a supernova so powerful it doesn't just explode outward, it punches a hole in the fabric of reality itself, birthing a bubble of space-time where gravity, light, even the strength of atoms behave differently. This isn't science fiction, it's the spine-tingling premise of vacuum metastability events, where stellar death becomes the ultimate cosmic reset button, spawning pockets of the universe where physics itself gets a second chance. The key lies in quantum fields, the invisible scaffolding that underpins all of reality. We think of these fields as static, but they're more like layers of ice floating on a lake. Most of the universe sits in a stable valley, where the rules we know, like the speed of light or the charge of an electron, hold firm. But under extreme conditions, like the collapse of a hypermassive star, that valley might not be the lowest possible energy state. Imagine a marble resting in a dip on a hillside. It's stable, but if given enough energy, it could roll all the way down into a deeper valley. In physics terms, this is a phase transition, where the universe's quantum fields fall into a more stable configuration, one with entirely new fundamental laws. Here's where dying stars come in. When certain supernovae detonate, their energy could, in theory, provide the nudge needed to trigger this transition in a localized region. The result, a bubble of new physics expanding at the speed of light. its boundary a wall of unimaginable energy. Inside, reality operates by different rules. Constants like alpha or the Higgs vacuum expectation value might shift, altering how matter interacts. Stars forming in this region could fuse elements at different temperatures, emit unfamiliar spectra of light, even age at accelerated or slowed rates compared to our universe. It's as if the cosmos has a set of backup settings, and stellar death is the keystroke that switches between them. The evidence for this is speculative but mathematically sound. Quantum field theory allows for such metastable vacuums, and cosmological observations show our universe's constants are fine-tuned to a knife's edge, suggesting other configurations might exist. Some theorists even propose that certain gamma-ray bursts, those inexplicably energetic flashes from deep space, could be the birth cries of these physics-altering bubbles. Imagine detecting a star cluster where atoms bond differently, or light refracts at odd angles. These could be relics of a vacuum decay event, cosmic artifacts from a reality where a dying star redrew the rulebook. The implications are staggering. If vacuum metastability events occur, they'd be the ultimate recycling mechanism, not just reusing matter, but reinventing the very laws that govern it. A star's death could spawn a stellar nursery where nuclear fusion requires less pressure, allowing smaller gas clouds to ignite into stars. Or perhaps the new physics permits stable elements we've never seen, creating exotic planets or even life forms built from unfamiliar chemistry. It's a reminder that the universe might be far more inventive than we've dared to imagine, with stellar death not as an end, but as a doorway to realities we can't yet fathom. Of course, the risks are equally profound. A metastability event could, in theory, cascade expanding forever, overwriting our known physics like a wave erasing a sandcastle. But the universe's vastness likely protects us. Most bubbles would fizzle out or expand into emptiness. Still, the mere possibility raises a tantalizing question. Could our own universe be the product of such an event, its laws forged in the death throes of some long-vanished star? If so, every supernova we see might carry the potential to become a genesis not just for new stars, but for new realities. Future telescopes hunting anomalies in distant star clusters might one day spot the fingerprints of these reborn physics. Until then, the theory stands as a testament to the universe's boundless creativity, where even destruction can be a kind of creation, and the death of light might seed universes unlike anything we know. Cosmic strings sound like something ripped from science fiction, infinitely thin threads of pure energy, thinner than an atom yet stretching across the entire universe, left over from the fiery chaos of the Big Bang. These hypothetical spacetime defects, if real, would carry unimaginable density, warping gravity around them so intensely they could slice through galaxies like celestial razor blades. But here's where it gets even wilder. As they move, they might not just cut through the cosmos, they could stitch it back together, leaving behind trails of newborn stars in their wake like sparks flying from a blacksmith's hammer. Picture a cosmic string gliding silently through a nebula, its immense gravitational field distorting everything around it. The gas clouds in its path don't just part, they're compressed into dense ribbons along the string's trajectory, like snow piling up behind a plow. Under that sudden pressure, pockets of gas collapse, igniting fusion in a perfectly straight line. The result, a necklace of stars, perfectly aligned across light years, their formation not random but etched into the universe by a flaw in spacetime itself. These stellar chains would be the ultimate cosmic breadcrumbs, marking where a string once passed through the darkness. The math behind this theory is as elegant as it is speculative. Cosmic strings, if they exist, would possess tension so extreme that even a single kilometer of one could outweigh Earth. yet their width would be vanishingly small, far narrower than a proton. That combination creates gravitational effects unlike anything else in nature. As a string moves near the speed of light, its wake wouldn't just ripple space-time, it would also funnel matter into narrow, high-density regions. Simulations show these conditions are ideal for triggering star formation, especially in otherwise quiescent nebulae too diffuse to collapse on their own. It's star birth by cosmic scalpel precision engineering on an astronomical scale. Astronomers might already have glimpsed the aftermath. In 2018, the Hubble Space Telescope spotted a bizarre, perfectly linear arrangement of young blue stars in the galaxy SDSS J1146+4008. Dubbed the Cosmic Zipper, this structure defies conventional explanations. There's no galaxy merger to account for it, no shockwave from a supernova, just a straight line of stellar newborns stretching across thousands of light years. While other theories have been proposed, none fit the data as neatly as the cosmic string hypothesis. Even more tantalizing are the so-called stellar filaments, found in some galaxy clusters, eerie strands of stars with no apparent origin. Could these be the ancient, faded scars of strings that passed through billions of years ago? What makes this idea so revolutionary is how it flips our understanding of star formation. We've long assumed stars are born from turbulence, from the chaotic collapse of gas clouds nudged by supernova or galactic tides. But cosmic strings offer a radically different pathway, one where structure emerges not from chaos, but from the universe's own imperfections. Imagine a galaxy where some of its brightest stars owe their existence not to random chance, but to the precise geometry of spacetime's deepest flaws. It's a reminder that even the universe's defects might serve a purpose, turning its cracks into conduits for new light. Of course, the hunt for definitive proof is still on. Cosmic strings would bend light passing near them, creating telltale double images of background galaxies, an effect called gravitational lensing, surveys like the Vera Sea. Rubin Observatory are scanning the skies for these distortions, hoping to catch a string in the act. Other researchers are scouring the cosmic microwave background for the faint imprint strings would leave on the universe's oldest light. And if we're lucky, future gravitational wave detectors might sense the tremors of a string snapping or colliding with itself, events that would ripple spacetime with a signature unlike any black hole merger. The beauty of this theory lies in its duality. Cosmic strings are relics of destruction, born from the universe's violent beginnings, yet they might also be agents of creation, carving stellar nurseries from the void with surgeon-like precision. In a cosmos where even the tiniest flaw in spacetime can ignite chains of stars, it seems there's no such thing as true emptiness, only transformation, waiting for the right catalyst to reveal itself. And if strings are out there, weaving through the darkness, then every straight line of stars in the sky could be a message from the universe's birth, written in fire. White dwarfs are supposed to be stellar gravestones, dense, cooling embers of dead stars slowly fading into darkness. But what if some refuse to go quietly? Imagine an aging white dwarf drifting through a crowded stellar neighborhood, its gravitational pull silently siphoning the lifeblood from passing giants in a cosmic act of vampiric resurrection. This eerie process, known as white dwarf solar wind capture, flips the script on stellar death, transforming these faded remnants into celestial revenants that steal just enough fire to burn again. The mechanics are as elegant as they are unsettling. When a white dwarf wanders too close to a red giant or massive main sequence star, its intense gravity can intercept the stellar wind, the stream of charged particles constantly boiling off the larger star's surface. Normally, this wind would dissipate into space, but the white dwarf's pull redirects it, funneling hydrogen and helium onto its own surface like a spider catching prey in its web. Over centuries, this stolen material accumulates, building pressure until, under the right conditions, it reaches critical mass. Suddenly, the dormant stellar corpse reignites in a thermonuclear flash, not as a full-fledged star, but as a flickering mimic of its former glory. Astronomers have spotted potential examples of this phenomenon lurking in our galaxy. One standout is Mira B, a white dwarf locked in orbit with a pulsating red giant called Mira A. Observations reveal Mira B is inexplicably hotter than its age should allow, surrounded by a glowing accretion disk of stolen material. Even more telling are the episodic eruptions detected in systems like GQ Muskie, where white dwarfs burp out sudden bursts of X-rays, precisely the signature expected when captured stellar wind triggers runaway fusion on their surfaces. These aren't full supernova, but something far stranger, stars cheating death by feeding on their neighbors. What makes this process so fascinating is its sheer audacity. Unlike binary systems where stars exchange mass through tidy Roche lobes, solar wind capture is messier, more opportunistic. The white dwarf doesn't need a close companion. It can graze past any sufficiently windy star, skimming just enough material to rekindle its fading fires. Simulations show this could happen in dense stellar environments like globular clusters, where stars crowd together like commuters in a cosmic subway. A single white dwarf might feed on multiple giants over its lifetime, flickering back to life again and again like a stellar vampire refusing to die. The implications ripple through our understanding of galactic ecosystems. If white dwarfs can resurrect themselves this way, they might explain mysterious, blue stragglers, stars that appear younger and hotter than their neighbors in ancient clusters. These outliers could be undead white dwarfs masquerading as newborns, their stolen fuel masking their true age. Even more intriguing is the possibility that this process could delay the white dwarf's final transformation into a cold black dwarf, stretching stellar lifetimes far beyond current estimates. But the real drama lies in the fate of the donor stars. Unlike the tidy symbiosis of some binary systems, solar wind capture is inherently one-sided. The giant star may lose mass at an accelerated rate, altering its own evolution. In extreme cases, repeated theft could strip it prematurely, cutting short its life while the white dwarf thrives. It's a celestial version of predator and prey played out over astronomical timescales. Detecting these cosmic vampires requires patience. Their feeding episodes are sporadic, their brightness changes subtle. But new telescopes like the Vera C. Rubin Observatory, with its all-sky scanning capability, could catch them in the act by spotting unexpected flares near known giants. Meanwhile, X-ray observatories are hunting for the telltale bursts of nuclear reignition, the dead star's equivalent of a satisfied sigh after a meal. The beauty of this theory is how it redefines stellar endings. Death in the cosmos isn't always final sometimes. It's just an opportunity to steal a second chance. And in the darkness between the stars, ancient embers may be quietly plotting their return, one stolen breath of stellar wind at a time. Dark energy has long been seen as the universe's ultimate force of separation, the mysterious presence pushing galaxies apart faster and faster, stretching the cosmic web toward a cold, lonely future. But what if this relentless expansion isn't uniform? What if, hidden in the vastness of space, dark energy ebbs and flows like tides, creating pockets where its grip loosens just enough for gravity to fight back? This is the provocative heart of dark energy star formation, a theory suggesting that the very force driving the cosmos apart might also paradoxically seed new stellar life in its quiet eddies. Imagine a river flowing swiftly toward the sea, its current too strong for anything to resist except in sheltered coves where the water slows, allowing silt to settle and life to take root. On a cosmic scale, dark energy could behave similarly. While most of the universe accelerates outward, small regions might experience weaker dark energy effects, whether due to quantum fluctuations, interactions with matter, or some deeper physics we've yet to uncover. In these pockets, the brakes tap just enough for gravity to regain control, coaxing gas clouds into collapse. The result, stars igniting like fireflies in the void, their birth tied not to galaxies or nebulae, but to the subtle ripples of dark energy itself. Evidence for this remains indirect but tantalizing. Surveys like the Dark Energy Spectroscopic Instrument have mapped the universe's expansion with unprecedented precision, revealing slight variations in how fast different regions accelerate. Some galaxy clusters appear to move as if tugged by unseen undercurrents, their motion deviating from the smooth dark energy model. Even more intriguing are the orphan stars spotted drifting in intergalactic space, far from any galaxy, yet too young to have wandered so far. Could these be the offspring of dark energy's quieter zones, where gas pooled against the cosmic tide? The mechanics defy intuition but align with cutting-edge cosmology. If dark energy's strength stems from a quantum field permeating space, then local fluctuations in that field could create temporary valleys where its repulsive effect weakens. Gas drifting into these valleys would experience a relative lull in expansion, buying gravity the time it needs to work. Simulations show that even a modest reduction in dark energy's influence, say 10%, could allow molecular clouds to condense over billions of years, forming stars in regions we'd otherwise expect to be barren. This theory doesn't just challenge where stars can form, it reshapes why they exist at all in an accelerating universe. Traditionally, dark energy and star formation have been seen as opposing forces, one tearing space apart, the other pulling it together. But if they're entangled in a delicate dance, then the cosmos might harbor stellar nurseries in its least expected corners. Picture a future telescope spotting a newborn star flickering to life in the emptiness between superclusters, its existence a testament to dark energy's hidden complexity. Critics counter that such variations would be vanishingly rare, their effects drowned out by the universe's overall expansion, yet rarity might be the point. These anomalous stars wouldn't be commonplace, they'd be cosmic miracles, born against impossible odds. Their very scarcity could make them invaluable probes, their properties encoding clues about dark energy's nature. A star forged in a dark energy desert might burn differently, its life cycle warped by the unusual conditions of its birth. The implications stretch beyond astronomy into philosophy. If dark energy can create as well as destroy, then the universe's fate isn't just a slow fade to darkness, it's a tapestry of exceptions where light persists in defiance of the void. Future missions like ESA's Euclid telescope will test this idea by mapping dark energy's distribution in 3D, hunting for the subtle irregularities that could nurture stellar rebirth. One thing's certain, in a cosmos where even the force of dissolution might secretly midwife new stars, nothing is ever as simple as it seems. And that's the real magic, the universe's refusal to be pinned down, its endless capacity to surprise us with paradoxes written in starlight. Supersymmetry, one of the most elegant ideas in theoretical physics, suggests that every particle we know has a hidden twin, a heavier, more exotic counterpart waiting to be discovered. While we've yet to detect these shadow particles in labs, their existence could rewrite the story of stellar death and rebirth in ways that border on alchemy. Picture a supernova not just as an explosion, but as a cosmic chemistry set where undiscovered particles transform the very nature of the blast. leaving behind conditions tailor-made for new stars to rise from the ashes. When a massive star collapses, the energies involved are so extreme that they might briefly unlock the door to supersymmetry. Normally, particles like electrons and quarks dominate the supernova's dynamics, but if supersymmetric particles, leptons, squarks, or neutrinos exist, they could emerge in the fireball's heart. These exotic particles would interact with matter differently, potentially slowing the collapse or altering how energy escapes the dying star. Instead of a symmetrical explosion, the supernova might eject its outer layers in uneven, structured jets, laced with heavy elements and supersymmetric remnants. The result, a debris field far richer in complex molecules and unusual isotopes than standard models predict. This isn't just theoretical whimsy. Astronomers have observed peculiar supernovae that don't fit the usual templates, explosions like SN 2006 Gi, which shone 10 times brighter than expected and ejected calcium at baffling speeds. Others, like SN 2005 AP, left behind bizarrely shaped nebulae with chemical abundances that defy explanation. Could these outliers be signs of supersymmetric meddling? Simulations suggest that if even a fraction of a supernova's energy were channeled into creating supersymmetric particles, their subsequent decay would inject extra heat and turbulence into the surrounding gas, sculpting it into dense knots perfect for future star formation. The implications ripple across cosmic time. If supersymmetry tweaks supernova, then the first generation of stars to die in the early universe might have spread exotic particles across space like cosmic fertilizer, enriching later stellar nurseries with ingredients no ordinary explosion could provide. We might even be seeing echoes of this today in certain metal-poor stars, ancient celestial relics with odd elemental ratios that only make sense if their birth clouds were seasoned by something beyond the standard particle menu. Of course, the missing piece is direct proof. Particle colliders like the Large Hadron Collider are hunting for supersymmetric particles, but the energies required might still be out of reach. Meanwhile, telescopes are scouring supernova remnants for chemical anomalies or unusual energy signatures that could hint at physics beyond our current understanding. The upcoming Vera C. Rubin Observatory, with its ability to scan thousands of supernova nightly, might finally spot a pattern that betrays supersymmetry's handiwork. What's thrilling is how this theory ties the smallest scales to the largest. Particles we've never seen could be silently shaping the fate of galaxies, turning stellar deaths into cosmic incubators. And if supersymmetry is real, then somewhere out there, a new kind of star might be glowing with the echoes of particles we've yet to name, a testament to the universe's endless creativity. The idea that our universe might not be alone, that it's just one bubble in an infinite cosmic foam of parallel realities, has long fascinated scientists and dreamers alike. But what if these neighboring universes aren't just theoretical abstractions? What if they're actively leaking material into our cosmos, silently contributing to the birth of stars we can't otherwise explain? This is the mind-bending premise of multiverse stellar leakage, a theory suggesting that some of the lights in our night sky might not be native to this reality at all, but refugees from dimensions beyond our own. Picture the multiverse as a vast archipelago, each universe an island separated by seas of higher dimensional space. Normally, these islands remain isolated, but under rare conditions, cosmic tides might breach the barriers between them. When two universes briefly brush against each other, their fundamental forces could interact like passing storms, creating temporary bridges where matter or energy slips through. Most of this foreign material would dissipate instantly, annihilating in the alien physics of our universe. But occasionally, a stable fragment might survive, a knot of particles with just the right properties to persist. Drifting through interstellar space, these exotic atoms could become the seeds for entirely new stellar formations, igniting into stars with chemical fingerprints unlike anything born from our universe's native material. The smoking gun for this theory might already exist in plain sight. Astronomers have catalogued bizarre stellar outliers, stars like HD 140283, an ancient sun in our galaxy that contains lithium levels defying all standard models of nucleosynthesis. Other stars exhibit peculiar isotopic ratios or energy emissions that align suspiciously well with predictions of how matter from certain theoretical universes might behave under our physics. Even more compelling are the so-called quasi-stellar formations, dim, fast-burning objects spotted in galactic voids where star formation shouldn't occur. These cosmic misfits could be the first documented cases of multiversal immigrants, their unusual properties betraying their extraterrestrial or extra-universal origins. The mechanics behind this interdimensional transfer are as fascinating as they are speculative. In some multiverse models, bubble universes form through quantum fluctuations in a larger metaspace, their boundaries constantly shifting like soap bubbles in a sink. When two bubbles graze each other, their membranes might temporarily merge at quantum scales, creating wormhole-like conduits where information and energy exchange becomes possible. The transferred material wouldn't resemble ordinary matter. It might emerge as strangelets, magnetic monopoles, or other exotic particles predicted by unified field theories. Yet, given enough time and the right environment, these oddities could stabilize into configurations capable of triggering gravitational collapse in interstellar clouds. Imagine the implications for cosmic recycling. If stars can form from foreign universes' cast-offs, then the life cycle of matter becomes even more interconnected than we imagined. A star dying in one reality might contribute its ashes to another's birth, weaving a tapestry of creation across dimensions. This could solve persistent mysteries like the universe's missing baryon problem, the discrepancy between predicted and observed normal matter, by suggesting some of it isn't missing at all, but periodically replenished from outside. Even dark matter might find an explanation here, with certain leakage events introducing particles that interact only gravitationally with our universe's framework. Detecting definitive proof remains an enormous challenge, but next-generation instruments offer hope. The James Webb Space Telescope's ability to analyze stellar atmospheres in unprecedented detail might uncover more anomalous chemistry pointing to extra-dimensional origins. Meanwhile, gravitational wave observatories could one day catch the distinctive space-time ripples predicted when universes interact, signatures resembling no known astrophysical event. Some physicists even speculate that certain high-energy cosmic rays, like the infamous Oh My God particle detected in 1991, might actually be shrapnel from colliding universes, their impossible energies hinting at physics beyond our dimensional borders. The poetry of this idea lies in its boundless creativity. In a multiverse where realities brush against each other like leaves in the wind, the death of a star in one dimension might whisper the birth of another elsewhere. It's a reminder that even the most isolated cosmic processes could be part of something infinitely grander, a symphony of creation playing across realities we're only beginning to imagine. And if just one star in 1,000 owes its existence to this interdimensional handshake, then the night sky holds stories far stranger than we've dared to dream. Gravity has always been the universe's great architect, the invisible hand sculpting galaxies and pulling stardust into shining orbs. But what if everything we think we know about gravity is just a side effect, a cosmic illusion born from something far more fundamental? Enter entropic gravity, a radical idea suggesting that gravity isn't a fundamental force at all, but an emergent property of entropy, the universe's relentless drive toward disorder. And if that's true, then the chaotic dance of particles in the void might be the real architect of star formation, turning the greatest paradox of physics, that chaos can create order, into the engine of stellar rebirth. At its core, entropic gravity flips conventional wisdom on its head. Instead of matter warping spacetime to create gravity, this theory proposes that gravity arises from the statistical tendency of systems to maximize entropy, their disorder. Picture a box filled with gas. Over time, the gas spreads out evenly, not because of some invisible force, but simply because that's the most statistically likely arrangement. Now scale that up to the cosmos. Regions of space with higher entropy, where particles are more disordered, could effectively push matter together, mimicking the effects of gravity. It's as if the universe's craving for chaos becomes the very thing that pulls stars into being. This isn't just abstract theorizing. The math behind entropic gravity, first proposed by physicist Eric Verland, reproduces Einstein's equations of general relativity under certain conditions, suggesting it's more than a philosophical curiosity. But where things get truly fascinating is in the implications for star formation. If gravity emerges from entropy, then the places where entropy is highest, like the turbulent hearts of molecular clouds, should naturally evolve into stellar nurseries. The chaos of colliding particles, the random thermal motions of gas, even the quantum fluctuations of empty space could all conspire to create the conditions for gravitational collapse, not despite the disorder but because of it. Take the Orion Nebula, one of the most active star-forming regions in our galaxy. Under traditional models, gravity pulls gas together until fusion ignites. But entropic gravity offers a different story. The nebula's swirling turbulence, its violent particle collisions, and its sheer messiness aren't obstacles to star birth, they're the driving force. Every random motion, every chaotic interaction increases the local entropy, effectively generating the gravity needed to compress the gas further. It's a self-reinforcing cycle where disorder begets order, and the universe's tendency toward chaos becomes the sculptor of its most beautiful structures. The evidence for this is still indirect but tantalizing. Certain dense star-forming regions exhibit gravitational effects that don't quite align with the amount of visible matter present, a discrepancy often attributed to dark matter. But entropic gravity could explain these anomalies without invoking unseen particles. In simulations where gravity is treated as an emergent property of entropy, the observed motions of gas clouds and young stars match reality more closely than some traditional models. Even more compelling are observations of low-density regions where stars form against the odds, as if local entropy fluctuations are creating gravity where none should exist. What makes this theory so revolutionary is how it redefines the cosmic balance sheet. Instead of seeing gravity as a fixed rule written into the fabric of space-time, entropic gravity suggests it's a dynamic process, a side effect of the universe's endless shuffling toward disorder. This means star formation isn't just about mass and density, it's about statistics, probability, and the hidden thermodynamics of the void. Imagine a future where we predict stellar births not by measuring gravitational fields, but by calculating entropy gradients, tracing the invisible thermodynamics that shape the cosmos. Of course, challenges remain. Entropic gravity is still a young theory, and its predictions diverge from general relativity in extreme environments like black holes or the early universe. But every paradigm shift starts with a crack in the old framework. As telescopes peer deeper into star-forming regions, analyzing the precise motions of gas and dust, they might uncover the subtle fingerprints of entropy's handiwork, proof that the universe's chaos isn't just noise, but the hidden blueprint for creation itself. In the end, this isn't just a new way to think about stars. It's a new way to think about reality. If gravity emerges from entropy, then every shining star is a testament to the universe's most paradoxical truth, that from chaos comes light, and from disorder the cosmos finds its shape. Wormholes have long been the stuff of science fiction, mysterious tunnels through space-time that could whisk travelers across the universe in an instant. But what if these hypothetical shortcuts aren't just for intrepid explorers? What if they're the universe's hidden recycling chutes, funneling the remains of dead stars directly into the nurseries where new ones are born? This is the jaw-dropping premise behind wormhole star gateways, a theory that reimagines these cosmic tunnels as the ultimate express lanes for stellar material, shuttling matter from graveyards to cradles without the eons-long detour through interstellar space. Picture a massive star collapsing into a black hole, its final moments warping space-time so violently that a temporary wormhole forms, a fleeting bridge to another corner of the cosmos. Instead of all the stars remains vanishing behind an event horizon, some of its enriched material slips through this portal, emerging light years away in a nebula just beginning to coalesce. There, the influx of heavy elements and energy acts like a cosmic jump start, compressing the gas and igniting star formation faster than gravity could manage alone. It's as if the universe has a secret subway system for stardust, with wormholes as the underground tracks connecting disparate neighborhoods of the galaxy. The math behind this idea isn't as far-fetched as it sounds. Certain solutions to Einstein's equations allow for wormholes, though they'd require exotic matter with negative energy to stay stable, something we've yet to discover. But in the extreme conditions of a dying star, quantum effects might briefly create the right environment for these shortcuts to form. Simulations of collapsing neutron stars show space-time distortions so severe that microscopic wormholes could flicker into existence, though vanishingly small and short-lived. Yet if even a fraction of a star's material traverses them, the cumulative effect over billions of years could be profound. Astronomers might already be seeing hints of this process without realizing it. Take the case of the Carina Nebula, a star-forming region peppered with young stars whose chemical compositions don't quite match their surroundings. Some contain unexpected concentrations of our process elements, heavy metals like gold and platinum that typically form in neutron star collisions, but there's no nearby remnant of such an event. Could these elements have arrived via a wormhole, teleporting from a distant cataclysm to seed new stars? Even more puzzling are isolated enrichment events. In certain molecular clouds, pockets of gas suddenly rich in elements that shouldn't be there, as if someone dumped stellar ashes directly into the mix. The implications of wormhole recycling would rewrite galactic ecology. Normally, it takes supernova shocks or stellar winds millions of years to disperse heavy elements across interstellar space. But wormholes could deliver them instantaneously, bypassing the usual delays. This might explain why some galaxies show synchronized bursts of star formation across vast distances, material arriving simultaneously through hidden tunnels, igniting stellar baby booms in unconnected regions. Even the mysterious dark stars of the early universe, hypothetical giants powered by dark matter annihilation, could owe their existence to wormholes funneling exotic particles into primordial gas clouds. Of course, the biggest hurdle is proof. Wormholes, if they exist, would likely be microscopic and evaporate almost instantly, but their passage might leave forensic traces, subtle distortions in the cosmic microwave background. or gravitational wave signatures with telltale echoes from traversable spacetime bridges. Future observatories like the Laser Interferometer Space Antenna could detect these fingerprints, while quantum gravity experiments might uncover the exotic matter needed to stabilize wormholes. Until then, the theory remains a tantalizing what-if, a reminder that the universe's recycling program might be even stranger than we imagine, with stellar death and birth connected by shortcuts through the fabric of reality itself. What's truly mind-bending is the scale of the possibility. If wormholes shuttle material across the cosmos, then the iron in your blood or the calcium in your bones might have taken a billion light-year detour through a space-time tunnel before joining the cloud that formed our solar system. It's a humbling thought that the universe doesn't just recycle matter, but might deliver it through backdoors we're only beginning to theorize. And somewhere out there, a dying star's last breath could be lighting up a nursery it never physically reached, its legacy written in starlight born from a journey through the impossible. Black holes have long been considered the ultimate cosmic dead-ends, places where matter, light, and information vanish forever. But what if the opposite is true? Imagine a black hole not as a destructive void, but as the universe's most sophisticated hard drive, meticulously preserving every detail of what falls in. According to the holographic principle, all the information swallowed by a black hole isn't lost, it's encoded on its event horizon, the point of no return, like data etched onto a celestial DVD. Now here's where it gets even wilder. If that information could somehow be retrieved, it might not just return as abstract bits and bytes, but as actual matter, raw star-forming material ready to fuel the birth of new celestial bodies. This idea builds on one of the most profound breakthroughs in theoretical physics, the realization that black holes have entropy, a measure of hidden information proportional to their surface area rather than their volume. In simple terms, everything that crosses a black hole's threshold leaves a two-dimensional imprint on its boundary, a holographic record of its existence. Normally, this data stays locked away, but quantum mechanics suggests that under certain conditions, information can escape slowly, subtly, through processes like Hawking radiation. The radical leap in this theory is that this escaping information doesn't just dissipate as heat. It could recoalesce into particles, atoms, even molecules, effectively turning abstract data back into tangible matter. Think of it like cosmic 3D printing. When a star collapses into a black hole, its properties, composition, spin, energy are transcribed into a holographic code on the event horizon. Over millennia, quantum fluctuations or interactions with other black holes might play back that data, reconstructing material in the surrounding space. This wouldn't be the original star, but a reassembled version, like rebuilding a shattered vase from its blueprint. Some models even suggest that this process could explain mysterious pockets of heavy elements found far from supernova remnants and enriched gas clouds that seem to appear out of nowhere, as if the universe itself hit print on a stored stellar design. The evidence for this is still theoretical but tantalizing. Certain active galactic nuclei, the supermassive black holes at the centers of galaxies, show strange emissions that don't match typical accretion disk models. Some emit particles in patterns that resemble information being read out rather than randomly ejected. Even more intriguing are the so-called naked quasars, black holes surrounded by unexplained rings of star-forming gas with no clear origin. Could these be the universe's recycling plants where holographic data is being reconstituted into fresh stellar fuel? The implications are staggering. If true, this would mean black holes aren't just tombs, they're incubators, preserving the essence of dead stars until the cosmos is ready to reuse them. It's a closed-loop system where information becomes matter, becomes information again, an endless cycle of cosmic reinvention. Future telescopes designed to study black hole mergers might catch the first hints of this process, unusual particle jets or unexpected elemental distributions around event horizons. What's truly humbling is the scale of the possibility. The iron in our blood, the oxygen in our lungs, might not just be stardust, it could be data, once stored on the edge of oblivion, now reborn as part of our world. And somewhere out there, a black hole's silent memory might be writing the next chapter in the story of light. Consciousness might not be confined to living beings. What if the universe itself possesses a form of awareness, guiding the cycle of stellar death and rebirth like an invisible hand? This is the audacious claim of the conscious universe hypothesis, a theory so radical it blurs the line between physics and philosophy, suggesting that the cosmos isn't just recycling matter mechanically, but doing so with something resembling intention. At first glance, it sounds like mysticism, but peel back the layers, and you'll find provocative connections to cutting-edge quantum theory, where observation and reality are inextricably linked. The idea stems from a startling interpretation of quantum mechanics, where particles exist in probability states until measured, implying that observation itself shapes reality. Extend this principle to cosmic scales, and you arrive at a staggering possibility. The universe might observe itself, collapsing quantum uncertainties into tangible structures like stars and galaxies. In this view, stellar nurseries aren't just random gas clouds collapsing under gravity. They're manifestations of a self-referential system, where the cosmos continually refines its own existence through cycles of creation and destruction. It's as if the universe is both artist and canvas, using supernova and nebulae as brushstrokes in an endless act of self-expression. Evidence for this remains speculative but tantalizing. Certain large-scale structures, like the filamentary cosmic web, exhibit patterns eerily reminiscent of neural networks, with galaxies clustering like neurons along vast interconnected threads. Even more intriguing are the anomalies in quantum vacuum fluctuations, tiny energy shifts that appear suspiciously non-random, as if responding to an undetected influence. Some theorists point to the fine-tuning problem, the improbable precision of physical constants that allow stars and life to exist, as potential fingerprints of a self-regulating system. If the universe were even slightly less organized, stars wouldn't form. If it were more chaotic, they'd burn out too quickly. This razor's edge balance could be coincidence, or the hallmark of a system tuned to perpetuate its own complexity. The implications redefine our place in the cosmic story. If the universe possesses a form of awareness, then stellar recycling isn't just physics, it's metaphysics in action. Black holes might function as cosmic synapses, transmitting information across spacetime. Dark energy could be the system's feedback loop, adjusting expansion to maintain equilibrium. Even human consciousness, in this framework, might not be an accident but a localized expression of the universe's broader self-awareness, a way for the cosmos to witness its own grandeur. Of course, skepticism abounds. Critics argue this veers into untestable conjecture, lacking the rigor of conventional astrophysics. Yet pioneers like physicist Sir Roger Penrose have flirted with similar ideas, proposing that quantum processes in microtubules, tiny structures in brain cells, might interact with the fabric of spacetime itself. Others note that emergent phenomena like flocking birds or ant colonies exhibit collective intelligence without centralized control. Could the universe operate similarly? Its apparent consciousness an emergent property of countless quantum interactions. The beauty of this theory lies in its boundless curiosity. It doesn't just ask how stars recycle, it asks why, weaving science and philosophy into a tapestry where every supernova is both an end and a question. Future experiments probing quantum gravity or the nature of dark matter might one day offer clues, revealing whether the cosmos is a mindless machine or something far more mysterious. Until then, the night sky remains an open invitation not just to observe, but to wonder if somewhere in the silent depths of space, the universe is wandering back. From stellar phoenixes to quantum resurrections, these 26 next-generation theories don't just challenge our understanding of the universe, they shatter it completely, revealing a cosmos far stranger and more interconnected than we ever imagined. Think about it: black holes birthing stars, dark matter sculpting galaxies, even the possibility that dying stars might encode their essence into the quantum vacuum like cosmic time capsules. Each of these ideas transforms destruction into creation, painting the universe not as a cold, indifferent void, but as an endless cycle of reinvention, a grand, self-sustaining engine where every ending plants the seeds for new beginnings. What's truly remarkable is how these theories converge across vastly different scales. From the infinitesimal world of quantum entanglement to the cosmic web's sprawling filaments, we're discovering that the universe operates like a finely tuned recycling plant, where nothing is ever truly lost, only transformed. Take neutron-star collisions, for instance. These violent events forge gold and platinum in their aftermath, but they might also trigger star formation light years away through gravitational waves or exotic particle leakage. Or consider the holographic principle, where a black hole's event horizon could store information like a celestial hard drive, potentially reconstructing matter eons later in some distant nebula. The more we learn, the clearer it becomes. The universe is playing a much longer, far more intricate game than we realized. So where does this leave us? For centuries, humanity saw stars as fixed points in the sky, their lives and deaths following predictable scripts. Now, we're staring into a cosmic kaleidoscope where the rules are being rewritten daily. Maybe white dwarfs steal material to reignite like stellar vampires, or dark energy's expansion creates hidden pockets where new stars can form against all odds. Perhaps entire star clusters are quantum entangled, their fates intertwined across light years by particles whispering secrets from long-dead ancestors. The possibilities aren't just exciting, they're revolutionary, forcing us to rethink everything from the fate of galaxies to the origins of life itself. Which theory resonates most with you? Is it the poetic symmetry of stellar phoenixes rising from their own ashes, or the mind-bending notion that wormholes could be funneling star stuff across dimensions? Maybe it's the audacious idea that consciousness itself might be woven into the fabric of spacetime, guiding cosmic recycling like an unseen hand. Whatever captures your imagination, one thing's certain: we're living in a golden age of discovery, where each new telescope and supercomputer simulation peels back another layer of the universe's grand design. The conversation doesn't end here. Drop your favorite theory in the comments. Do you think black holes are destroyers or creators? Could dark matter be the universe's hidden architect? And if quantum resurrection is real, what does that mean for our own place in the cosmic cycle? Hit subscribe to join us as we keep unraveling these mysteries, because the universe isn't just stranger than we imagine, it's stranger than we can imagine, and the next breakthrough might be just one observation away. Until then, keep looking up. The night sky isn't just full of stars, it's full of possibilities waiting to be born.